Welcome to part 3 in personal renewable energy. To begin, let's examine several ways to interconnect PV panels for an inverter. We'll start by connecting the panels in parallel. Parallel connection means that we connect all of the positive terminals together, which is the red line, and all the negative terminals together, the black line. In parallel circuits, the currents add up. Imagine ideal panels producing 20 volts and 5 amps each. Therefore, if we add the panel currents, they add up to 4 panels at 5 amps, which equals 20 amps. In parallel, the voltages do not add. Therefore, it remains at 20 volts DC. Another way to connect PV panels is in series. In series connections, the negative terminals from each panel are connected to the positive terminals of the next panel. Series circuits are different from parallel in that the panel voltages add up while the current remains the same. If we add the panel voltages, they add up to 4 panels at 20 volts, which equals 80 volts. In series, the currents do not add up and therefore remains at 5 amps. We are familiar with series connections in the old style 6-volt battery-powered flashlights. Placing 4 times 1.5 volt batteries into the flashlight tube to add up to 6 volts. We have looked at both series and parallel connections, but imagine if we have 8 panels and we want the voltage from the panels to be 40 volts and the current to be 20 amps. How can we achieve this? Panels can be connected in combinations of parallel and series to achieve desired currents and voltages. This is important because connecting too many panels all in series might exceed the maximum voltage rating for the inverter, or connecting too many panels all in parallel might exceed the maximum current rating. In this example, the series connections are made from the negative terminals of the top panels connected to the positive terminals of the bottom panels. This means that the voltage in each series connection adds up to 40 volts. The parallel connections are made by connecting all the positive terminals together, shown on top, and all the negative terminals together, shown on the bottom. Connecting these in parallel means that the 4 currents will add up to 20 amps. In this example, the inverter will see a total voltage of 40 volts and a total current of 20 amps. If this seems a little difficult to grasp, think of the 2 panels in each column as a single 40 volt 5 amp panel instead of 2 separate 20 volt 5 amp panels. We have already looked at inverters in a previous video. Some inverters can also work with module level power electronics, or MLPEs. One type of these modules is called a DC optimizer and was made popular by SolarEdge, shown here. This unit is connected in the back of each PV panel. The optimizers perform maximum power point tracking, MPPT, at each panel. Compare this to an inverter that has to perform MPPT on the group of panels as a whole. Shadows or dirt on any panel can affect the entire system output, whereas having DC optimizers on each panel means that only the affected panel would have a lower output. This type of DC optimizer also performs a DC to DC conversion. This means that DC voltages normally coming from the panel are converted to an optimum DC voltage, so that when all the voltages are added up, it is the desired voltage the inverter wants to see. The trade-off from adding the cost of a module for each panel results in lowering the cost of the inverter, as it has no MPPT, and the inverter can be designed to operate over a very narrow voltage range, compared to regular inverters that must operate over a wide voltage swing. Another type of module is a micro-inverter. These are installed behind each panel, similar to DC optimizers. Microinverters have the same functionality as inverters, except that they are typically around 300 watts to match the power of the PV panel compared to 3 or 5 kilowatt inverters. Shown here are examples from Enphase and Darfon. While most microinverters are in a single package, shown here, there are also dual and quad packages to try to reduce the cost. Where an inverter is a single unit converting the DC to AC in one shot, microinverters convert DC to AC at each panel. One improvement is that aesthetically there is no inverter at eye level on an outside wall, as everything is on the rooftop. The output of each microinverter is 240 volts AC in North America or 230 volts AC in Europe. This shows how microinverters are connected using a trunk cable. The trunk cable sees a constant AC voltage, with the current increasing after each panel. One advantage is that they are ideal for smaller systems and can be scaled up. A homeowner can install a small number of panels and then easily add more panels at a later date. The wires from the microinverter trunk cables are identical to inverter wires connected to the electrical panel. The difference being, instead of DC traveling down wires from the PV panels to an inverter, a 230 or 240 volt AC travels down the side of the building into the house and to the electrical panel. We'll discuss some benefits of AC versus DC in another video. Thanks for watching.